Okay, good morning. So today is week 8. Okay, let me do some housekeeping first. There'll be no quiz on November 1st to 6th. Usually I have a quiz every week, but I learned from the last time if it's a term test coming on Saturday, having the quiz will not help because you guys are studying. So there's no quiz 6. Okay, so quiz 6 has been moved after. So quiz 6, if I look at time, okay, quiz 6 will be on. Hold on, let me inform you when quiz 6 will be held. So quiz 6. So next week is term test. Okay. So quiz 6 will be held on. Will hand in on November 19. Okay. Move to. Okay. So just to let you know, term test 2 will be next week. Okay. Again, the same like term test 1. Altogether, the entire length is 3 hours 15 minutes. But the actual writing time is 2 hours 30 minutes. Okay. The one you have to be too stressed when scanning. You have 45 minutes to scan. 12:15 is absolutely the drop time. Okay. There's no extension unless you have a blackout or anything. Okay. Topics to be covered from week 5 to week 8. So week 5, what we have is we have thin wall and longitudinal shear. Week 6 was reading week. Week 7 we had symmetrical centric bending, sandwich material under centric loading, which we will continue today, and the today's topic. Okay, so we're going to do example on sandwich material. We're going to look into sandwich material under axial loading. Then we have eccentric symmetrical loading cases and centric unsymmetrical loading. Okay, the fundamental part of it is still the same. The head of the vector arrow is compression. The tail end of the vector arrow is in tension. Still the same. So whatever analysis that we learned from last week, I know last week was a very long lecture in terms of writing, theory. Now it's all application. Okay. So last week we looked at sandwich material. So rather than to recall what I taught last week, let me do an example. Okay. And I believe by this example, you'll see things clearer, I hope. Okay. So the examples are all uploaded on Avenue to Learn. All this figure, please kindly download it on your own time. Okay. Or go to Avenue to Learn to download all these images. I don't want you to copy too much time. Right. So we are going to look into example number 1. So sandwich example on sandwich material. So this example, the top plate, okay, the top plate is made of aluminum. Okay, so we write down here that our top plate is made up of aluminum and it's used to reinforce a Kevlar plastic beam. Okay, so the rest of it, okay, the rest of it is Kevlar. Okay, Kevlar 49. Determine the maximum stress in the aluminum and in the Kevlar if the beam is subjected to a moment of 900 pound-feet. So what we have is 900 pound-feet of moment. And because our stresses are all in inches, we have to change this to pound inch. So this is equal to 900 multiplied by 12. So what we have over here is 10,800 pound inch. Okay, and if you look at the moment vector arrow, we know that the above the centroid will be compression, below will be tensile. All right. Why? Because it's a tail on of the moment vector. And then we look into the Young's modulus of aluminum. So the Young's modulus of aluminum is 10.6 times 10 to the power 3 psi. In term test, I will give you this value. Okay. Kevlar is 19.0 times 10 to the power 3 psi. Okay, so we know over here Kevlar is a material that has a higher Young's modulus. It's also equivalent to what we call stiffness. Okay, Kevlar has a higher stiffness than aluminum. So now the next thing we do is we're going to draw our transformation. So I'll call this X, this is Y, this is Z, based on the right hand rule. Okay, so the formula, the stresses we're going to find is in the X direction, right? So we know that the formula that we're going to apply is stress X, and we have a reference material coefficient, right? And then we know that moment is in the Z direction over IZZ multiplied by Y. Okay. So for this topic, we have to pick a reference material. Okay, we have to pick a reference. So for this case, I'm going to pick the reference material to be aluminum. Okay, we can pick Kevlar. The answer will be absolutely the same. Okay, so reference material is aluminum. Okay. So now we're going to calculate the coefficient. Okay, so N for aluminum is equal to E Young's modulus of aluminum divided by the reference material, which is E aluminum. This is equal to 1. Okay. Then the next thing we're going to look is we're going to do the coefficient, material coefficient of Kevlar. So E of Kevlar divided by Young's modulus of aluminum. So this will be equal to 19 times 10 to the power 6 divided by 10.6. Sorry, times 10 to the power 3, not 6, sorry. Yep, put times 10 to the power 3, yep. 10.6 times 10 to the power 3. So what they state, the value will be equal to 1.792. Okay, 1.792. Okay, let me sketch for you the original composite material geometry. Okay, so original composite material. Composite is also sandwich material. Okay. So what we have originally is we have a rectangular. Okay, so this is 12, 13 by 6. 2, 4, 6. Okay, 2, 4, 6, 8, 10, 12, 13. Okay, and then 0.5, 0.5, then we have layers of Kevlar. So what I'm drawing now is Kevlar. And then we have our aluminum. Okay, so this is our aluminum. The rest, everything is Kevlar. Okay, the rest, everything is Kevlar. So what we just did is when we do our analysis now, okay, we change everything to aluminum. Okay, so remember we just said that the reference material is aluminum. So what this means is we are going to change the entire structure into aluminum. Okay, so the Kevlar, we're going to change it to aluminum. So without compromising on its performance. I repeat again, without compromising the performance of the structure. So how is this possible? So the only way that this is possible is through size. Okay, artificially, okay, increasing the size. I repeat the term again, artificially. Okay, I mean in reality it's impossible. Okay, but in based on calculation, artificially it is possible. So what this means is we are going to keep the size of the aluminum the same. So I'm going to draw the aluminum the same size. Okay, aluminum the same size. And when you see, when I draw aluminum the same size, okay, this one is not so obvious yet. Okay, so this is our aluminum. Okay, so now we are going to increase the size of the Kevlar by how much? Okay, by 1.79 times. Okay, so how much is 1.79? So 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 20. So it's about approximately, okay. So now we are going to increase Kevlar, okay, by this size, which is I've just drawn, okay. So wait, 2, 4, 6, I'm in the right line, and we are going to increase Kevlar to this size now. Okay, so this is the size of our Kevlar now. And I want you to see something, okay? I want you to see something. So somewhere around here. So now this is the size of our Kevlar. Okay. So what is going on down here, as you can see, and I want to highlight this, okay? Now, I want to, you all really need to know this, and later on, I'll tell you mathematically what is going on, okay? So now the reference material is, as you can see, is our aluminum. So aluminum did not change in size at all. Aluminum is still the same what? Still the same size, right? You saw me, I just copied the image, right? So aluminum is still the same size, did not change. Now the Kevlar, right? Something changed. So what changed is the width. I repeat again, what changed is the width. Okay, so the width changed. The width has increased in geometry, but height, right? If